Okay, so we are looking at problem decomposition with goal trees. And we want to look at an algorithm which will solve it. So, what should the algorithm do? Break it down into simpler problems. And you keep doing this till the problems are trivially small or primitives that you have access to in some system essentially. Okay. So, we will use of course, one thing is to search the entire tree, but we do not want to do that. So, we will use a heuristic function which is estimated cost solving node n, and we will use the heuristic function to guide our search. So, let us say that we have some problem that we are trying to solve, and we compute the heuristic value, and let us say it is 50 essentially, just to start with essentially. So, when we start solving the problem, our estimate is that it is going to cost us 50 units of whatever, and let us assume for the sake of illustration here that every edge has a cost associated with it, which is 10 essentially. And let us say that I get something like this out of this. So, I get two edges out of it. One of them is a, you might say, a hyper edge or an AND edge, and the other one is a simple edge. So, this is a tree I get essentially. And let us say the cost associated with this is 15 and this is 20 and let us say this is 40 essentially. Now, in this example I have mixed up the kind of edges emanating from a node, and you can, if you think about this, it does not really cause a problem to see it like this. We can think of it as two choices at the top level, and this choice has already been broken down into two parts essentially. We could have easily transformed this into a node which says that 50 and then some node x and this is 40 and this x has got two nodes of course 15 and 20. These two are equivalent in nature, and we, if necessary we can always transform such a problem into that. Of course, we have to keep in mind the cost of the edges. So, we have to take care of that somehow, but for the illustration purposes here we will assume the cost of every edge is 10. So, if you have generated, so you have expanded, we will use the same term expanded a node. So, you have expanded the root or this thing and you have got these 3 nodes. So, which is the next node that one should pick? So, let me call them A, B and C. This is start node S, we will use similar terminology. So, between A, B and C, which is the next one I should expand? A. Why is it?
Cost of A is 40 plus 10 is S cost, but for B it is 20 plus 15 and plus 20 also.
Yeah. So, the cost of solving the original problem, if I take this option, would be the cost of solving this plus the edge cost, which is, so I can write this here 50, and the cost of solving it from the other side is 15 plus 20, 35 plus 20, which is 55. So, obviously, this is better. So, I must choose this side essentially. Then let us say I get this. Some values, and this is an AND node and this is an AND node. Then I can compute the cost of solving, revise the cost of solving A or my estimated cost of solving A. So, instead of 40 now this has become 30 plus 2 50 here, and this has become 40 plus 2 60 plus 20 60. So, 20 plus 20 plus 10 plus 10, so that is 60, and likewise this is 15 plus 10 for each arc, 60. So, I have to revise this cost now, this becomes 60 because this is 50 and this is 60, 50 plus 10 60 essentially. So, at this moment my algorithm must shift attention to the other side. So, you can see it has a best first nature about it. We are using a heuristic function to guide search. The heuristic function is the estimated cost of solving a node. It is just that because this is an AND OR graph or AND OR tree, we cannot make a decision based simply on the value of a node. We have to look at the cost of the full solution of which that node is a part essentially. Now, you can see that this is consistent with what we were doing earlier. We said that for example, when we are looking at the travelling salesman problem and the branch and bound algorithm, we are saying the estimate is the estimate of a full tour essentially and not just one that edges that we have found and so on essentially. So, now my attention must shift here and maybe I will expand one of these two nodes. So, let us say I expand this and let us say for argument's sake this can be solved like this, or it can be solved by another node which is of cost let us say 25. So, this is 20, this is 25, this is an OR node. So, this cost is, I have to revise this cost to 25 now, which means I have to revise this cost to 65, and then again my attention must shift this side essentially. So, basically what we need to do is to formalize this process and sort of make this a little bit clearer and put it down as an algorithm. So, let us try and write this algorithm. This algorithm is called AO star and it essentially finds a optimal solution for a problem like this. When do we terminate this process? So, let us say, see what has happened, this has now gone up to 65. So, we will shift our attention to this 60 and we will come down here. So, if I note, if I pick up, if I just name them, let us say D, E and F and G and H, what is the next node I should expand? So, I have to pick a leaf. Okay, so C is a leaf, H is a leaf, G, F, D, E. These I have already expanded. So, between D, E, F, G, H and C, which one should be the next node I should expand? Looking at the heuristic values. Okay, so just think about this. I will come back to this question in a moment. So, let us write this. So, A star works with a graph graph G, which is initialized to S, which is a single node S essentially, and then it says compute H of S and initialize Now, at any stage of the algorithm I will have a graph which looks like that essentially. I'll go into some sort of a loop while okay. So, we have this notion of a solved node and a node which is not completely solved. So, we saw for example, in the integration example the something like integral dw is a solved node or in the chemistry example we saw that once you know the complete structure of all the atoms you are talking about, it is a solved node. So, we will use a label called solved while, so as long as, and eventually we want to say that we have solved the original problem which is the root S essentially, and as and when we find a solution we want to percolate this label of solved up essentially. So, this is a problem decomposition process and there is going to be a secondary process in which some labels will travel upwards and one of the labels will be the solved label, and once the solved label reaches a root node we can say we have solved the root node essentially. So, while S is not solved, means it does not have a label solved, and okay. So, if you look at for example, Rich and Knight the book which describes this algorithm that I am describing here, we use some value called futility which says that basically we do not want a solution which is more expensive than this value. So, we are going to explore for a solution or look for a solution whose value is less than this number called futility essentially. So, that is just an additional thing that we are using. Do the following. Okay. So, we have to pick a node to expand. Of course, in the initial stage the graph has only one node, but at something like this stage the graph has evolved, and so let me get back to this question. I started by expanding this root node S, I got these 3 nodes, then because this was cheaper than these 2 combined I expanded this next, I got this option and this option. So, let us call the DE option and the FG option. The DE option costs 50, the FG option costs 60 and you add another 10 for this transformation. So, this becomes 50 plus 10 60 which is worse than 55. So, I came down this option. Now, here I chose between B and C 150, this B expanded that I got this 20 and 25, when I back up this values I got 25 here and that became 65. So, I have to now shift my attention to this one again because that is going down that path is estimated to cost 65, along this direction it costs 60. So, I must come down here. At this point I must choose this option because this estimated cost is 50 and here the estimated cost is 60. So, I must choose one of these 2 nodes for expansion next essentially. How do I do that? In the graph I maintain at every choice point a marker which marks the best choice at that point essentially or at that stage of the graph. So, for this graph at this stage I would have a marker here, here I would have a marker here because here this is a better choice, here this is a better choice, and here I would have a marker here. So, this algorithm is going to be a 2-stage process. In the first stage I will identify a node to be expanded and that I will do by starting from the root every time in every cycle in this while loop. We will start from the root, follow the markers and the markers will take us to a set of nodes and we have to pick a set of nodes. So, the forward phase is as follows, that follow the markers to a set of nodes, let us call them n, and then pick some If okay, pick some n belonging to n. So, we have picked the node. So, in this example I have to pick either D or E. Does it matter which one I pick next, whether I should pick D or whether I should pick E? So, in this example of course, both the costs are 15. So, obviously there is no way of telling which one I should pick, but let us say for some other example, this cost was 90 and this cost was 20. Let us say that D had a cost of 20 and E had a cost of 90, then of course they look different. So, will it matter if I pick D or if I pick E? So, you have to think of it from the perspective of reaching a solution and the perspective of saving on some amount of work. See, if in a OR graph when we are searching something like A star, if you have to choose between two nodes and you chose one, then you are committed to having a solution through that node essentially. I mean, if that happened to be the cheapest essentially. In an AO graph or AND/OR graph, if you are at an AND choice like this, if the solution is along this direction, you will have to eventually solve D and you will have to solve E also. So, you will have to solve both of them essentially. So, from that point of view, it does not matter whether you pick D or whether you pick E, because you have to solve both. If you have to solve, if the solution lies, if the subtree lies somewhere here. So, that is one perspective, but supposing these are the values 20 and 90, is there some other reason for trying to solve one of them? Now, you can think of this as, if you are solving a CNF kind of a formula, then you are exploring whether a sub formula, let us say F1 and F2, you have to try to solve both. So, if you have to solve for this formula which has F1 and F2, you have to solve F1 and you have to solve F2. So, it is not necessarily CNF, it is some formula, and of course, F1 and F2 are themselves compound formulas. If by looking at the size of those formulas, does it make sense to choose something which looks harder or something which looks cheaper essentially? So, this is the same problem here. Here D looks cheap, E looks expensive. Does the estimated cost, should it influence my choice? Having said that, I have to solve both anyway essentially. How will it help?
If the answer is rejected, then we don't need to compute the other one.
No.
But you could
So, you are not listening to what I am saying.
based on expense.
If you solve D, you have to also solve E. Why? Because this is an AND node here.
But if D does not give a solution,
Then
E and
you do not have to solve E.
you don't have to solve D.
Then which one is not likely to give a solution?
E.
The more expensive one, I think. Or if you keep in mind the fact that we have some bound on the cost of the solution that we are looking for. So, if you have to do two things anyway and your success depends on doing both the things, and if one of them is harder, then you should see whether you can do that harder thing first, because then you hope of solving the easier thing later essentially. The idea being that if you solve for D and then if you solve for E and then the solution cost shoots up, then you will have to anyway shift attention to the other side essentially. So, that extra work would be wasted essentially. Whereas, if you try to solve the more expensive thing first, then you will get to know early whether it is too expensive or not. So, that is the only idea, but if you have to solve for both, you have to solve for both. So, we will just assume pick some node n from n, generate children C of n So, we have something like a move gen function, which is not the old move gen function, but something which refines the problem into different sub problems and gives you the set essentially. If none, if I do not have, if this node n does not have any children, my system is not giving a child, which means my system is not telling me that I can decompose it in some way. What should I do? So, let us say I have picked this node n. So, let us say this is my node n that I have picked for illustration purposes, and now I am saying generate the children of n, which means if it has further solutions, expand it essentially. What if there are no children? What if this cannot be expanded? What if it is a dead end of some sort? What should my search do? If I cannot expand this, I do not find a solution, what should my search do? No, you have to speak up a bit, I can't hear. What does backtracking mean here?
Discard this.
Should I go and look at E then?
No.
Then
Go to previous.
I should somehow abandon this whole solution of which this is a part, because if I cannot solve D, then I cannot compose this solution which has D and E as their parts. So, I should abandon the whole thing. How do I do that? I simply say the cost of solving n is futility, because my algorithm is only looking for something which is less than futility, which means that this will never be considered henceforth essentially. Okay. So, generate children C of n, if none then you do this, then you remove loops. What do I mean by this remove loops? I am talking in the perspective of AND or graph. See, in the OR graphs, of course, we have this notion of looping, that you could just go around the same paths. Here, what does looping mean? And remember that AND OR problem is decomposing the problem into simpler problems. So, if you think of, for example, the symbolic integration that we looked at, can we have looping? How can we have? What do you mean by looping? Can we have looping when you are decomposing a problem? You said, you nodded your head.
In integration, it could happen like when we apply that formula, we will get the same integral part again.
So, it is possible that you do one transformation, you take sine by 4 by cos by 4, sine raised to 4 divided by cos raised to 4, and you get tan raised to 4, and then you apply another transformation which will, let us say, take you back to the same thing. So, it is possible, looping is possible, because you can, transformations are not one way, transformations can be two way in many situations. So, you want to avoid that extra transformation. So, that is probably mean by loops essentially. Then otherwise add for each child C belonging to this C, compute H of C. So, this is a forward phase of the algorithm, that in this situation I follow the markers, I will come to a set of nodes n. So, in this example n is these two nodes D and E, then I say pick some node n from this set, I have picked D from there, and then I think generate the children of this C. So, this is my set C, and this is the values. So, let us say I have two choices for solving D, and let us, for argument's sake, that each of them is 10 and this is 5 and 5, let us say, for argument's sake. So, what I am saying is that for each child C belonging to this set of children C, this set is C. For each child in this, compute the H values. So, this completes a forward phase essentially. Now, in the backward phase I have to propagate the new cost up essentially, and I have to readjust the pointers as I the markers as I go along essentially. So, that is a second phase. So, forward phase goes from the root to the leaves, the backward phase goes from this set C, a subset of the leaves, to the root essentially. So, what do I want to do? I want to I found these heuristic values 10, 10 and 5, 5. Now, I want to first change the heuristic value of n essentially. So, this is 10 and 10, 20 plus another 20, this becomes 40, and this is 5 and 5, 10 and plus 20, this becomes 30. So, I have to now say that the revised value of this node D is 30, and this is the best path to follow if you are solving this node D. So, I have to put this marker here and I have to revise it to 30. Okay. So, this is a new value that. So, these two things I have to do, correct. So, so this was my node n, I expanded this, I got these children, I evaluated the heuristic values, and now I have to propagate this value up till what. So, till what stage should this propagation go? It should go till as long as this node changes. If this node changes, then I must propagate its value to its parents essentially. So, let me take another situation. Or this one. Let us say this is a node that I have solved, and let us say this is 10, 5, or let us say this is 30, 5, 5, and this is 5, and this is 10, and let us say this was my node n. I just want to illustrate this idea. If this was my node n and these are the two children, I will evaluate these children, and what is the best way of solving this n? I will mark with a pointer and compute the cost. This is 5 plus 10, 15, and this is 10 plus 10 is 20. So, that is not the best one, this is the best one, and because this has changed from 5 to 15, I will add its parent here. So, this has become 5 plus 5, sorry 15 plus 5, 20 plus 20, which is 40, and this is, this was originally also 40 because this is 30 plus 140. Let us say this was 80 to start with, otherwise I would not have gone there at all. So, if this was 80, this is now 90. Now, after I have revised this, I must revise its parent, because its parent is getting affected, it has got from 20 to 40, and because I am revising this, I must revise both the parents. I must, because I know that this the cost of this has changed, this cost must be propagated to this as well. Whether I came from this path or whether I came from this path, it does not matter. I must revise both the parents. So, the process of propagation is basically to go up to all the parents essentially. Okay. So, if you have got a feel of that, let us write it down. So, let M be the set of nodes that have changed. This is just a comment. So, initialize M so the node that I expanded, I put this into the set M essentially, and essentially M is going to be the nodes whose value has changed essentially. So, I could have done the next steps before this, but it does not matter. So, let me write it here. It says that compute the best cost of n. Okay, let us say pick so let's say this node is P or something like that, or just to be consistent, let me use n, or I do not know which is better, let me use n, okay, because I have just only put n into this M initially. So, I will just use the same name exactly, but of course, as M grows it may have more elements. How will it grow? Because parents will get added to this set M essentially, but initially of course, there is only n inside M, and I am just simply saying using the same name saying pick some node M from n, compute best cost for n. How do I compute best cost for n? So, for example, if this was n, then I can see that from this side the cost is 40 and from this side the cost is 30. So, the best cost for n is 30 essentially. And I should have a check that anyway you are going to revise the cost irrespective of whether it improves or not essentially. So, compute the best cost for n if so I must do another thing here before that. For each child C, compute h of C, I must have another step which says that if C is primitive, label C solved. If the child that I have just generated is a terminal node or primitive or trivial or whatever you want to call it or solved, then put a label solved for that node C. So, for example, if this was solved, then I could just put a label saying solved, if I knew that this was solved node. The others may still have to be expanded and so on. So, for every child you compute the h value, and if it is a solved node or primitive node, you label it as solved, and then n is a node that we just expanded and we have added this to the set M, and we are picking some node from M. In this case it is only n to start with. Compute the best cost for n which has changed if a solution below is labeled solved, label n solved, where I should not say a solution, if the best solution. So, if the best solution below it is labeled solved, you label it solved. So, if I take this example again, the other side, supposing this was n, this is a better node. If this is solved, so I will use double circle to denote a solved node. If this is solved, so what do I need to do? I need to update n from 5 to 15, that is the new cost, that is the best cost for solving n. Initially I thought it was going to cost 5, but after I expanded it I know that either I have the choice of 15 or a choice of 20. the best cost is 15, but this is labeled solved. So, I must label this also as solved, that is a step here. If the best solution below it is labeled solved, then label that node solved. If I have to label this node solved, then the better solution, which is this side, both of them must be labeled solved. If both of them are labeled solved, then I can push the solved label here. So, in this fashion the solved label will percolate up, and I want to keep doing this till solved does not reach the root node essentially, and this is a mechanism for the backward phase. So, if the best solution below n is solved, then you put label as n solved. So, we have done two things, compute best and possibly labeled it solved. So, if any of these things happens, we will say that node n has changed, which means it was 15 originally, it has either changed to 30 in this case. In this example, it has changed to from 5 to 15, and also it has got a label solved essentially. So, either a change of heuristic value or the application of solved label means that the node has changed, and if a node has changed, so I am using this as a kind of a technical term that you have to have a test for doing it. If n has changed, then add all parents of n to n. So, all parents, that is what I was trying to illustrate here, is that if this has changed and this will change, if this changes, that not only must you propagate the change of cost from the direction you came, but also to any other parent that this may have essentially, because at a future date that parent might become essentially. So, I must put this of course in a loop while m is not equal to empty. I have this whole loop, pick some node from m, compute its revised value, which is the best value from all the sub solutions it has. If the best solution below it is labeled solved, label that node solved, and if the node has changed, add its parents to m essentially. So, what will happen, initially I will add only this node n to m, because it has changed I will add this parent here also, and because this has changed I will add this parent. In this way the revised value will propagate up. In this example, if this has changed, I will get a new label solved. So, I will add this to m, but this cannot be labeled solved because that branch still is unsolved. So, I will not label this solved, but I will change its value, because now it was originally 20 and now this has become 15 plus 5, 20 plus 20, 40. So, from 20 it has got to 40. So, it is changed. So, I must add both its parent to solve, they will change to m, they will change and I will add root to m, and after I change m I will add nothing to m, and eventually all these m's will get revised and this loop will terminate, which means the backward phase will terminate. So, the algorithm works in two phases. In the forward phase you move forward following the markers. Okay. So, I have missed out one step here. Somewhere here I must have this thing mark best sub solution, or I should say hyper edge, because each of these are the two hyper edges, just mark the best one. So, whenever you are looking at a node m, node in this m, you must recompute its value, which you will get from its children. You must mark the best path, because next time you go in the forward phase you must know which direction to go, and you must also percolate this solved label back if possible essentially, and it is possible if all the sub solution, if this entire hyper edge has nodes which are labeled solved essentially. So, just to repeat, if this was to be labeled solved and this was to be labeled solved, then this will get labeled solved. If this was to be labeled solved and this was to be labeled solved, then this will get labeled solved. The moment this gets labeled solved, if this is the best one, if the arrow is still pointing to this, that will get labeled solved, and then you will stop. In this example, this has got labeled solved, so this will get labeled solved, but this will not get labeled solved unless that gets labeled solved, and this is a better choice. So, I must have a marker here, there is a marker here. Once this gets labeled, if this was to get labeled solved and the marker was still here, then I can label this solved, and so on essentially. So, in the forward phase, you follow the markers, end up with some unsolved set of nodes, which we have called as this n. We pick some node from n, maybe the most expensive as we discussed a little bit earlier, but that is not really so important, but we pick some node from n, generate its children. If none, we call it futility, we assign the cost futility to that, then we remove loops, and for each child we compute the h values, that is this set of nodes here, or it could be this set of nodes here depending on what is n. So, that is there the forward phase ends, then you add this node n that you just expanded to this set m, initialize m to this set n, and then one by one you pick. Okay. So, this is not correct, this sum is not correct, I should say to pick the lowest. So, you can construct examples to show that you have to make this choice. So, if m is a collection of nodes, pick the one which is lowest in terms of the graph, pick the lowest node, compute its best cost below that. If the best cost leads to label to solve nodes, then label this node solved, and if either it has got label solved or if its cost has changed, you must add its parents to m, and this loop here, this whole loop here works under the condition as long as m is not equal to empty, you pick some node and do this process essentially, and that process is essentially backing up the values from the leaves towards the root node essentially. So, once this ends, the algorithm will go back to the forward mode, again follow the marked paths, again expand some node, then it will go into the backward phase, backing up the values from there. This forward and backward phase will keep happening till either one of the two things happens, that either the value solved is percolated to the root or the value of futility is percolated to the root essentially. So, in which case either it will give you a solution would be a sub graph or a sub tree, or it will say that we cannot find a solution of this cost. So, there is only one more point left. For this algorithm to be called AO star, for it to deserve the suffix of star, we need a condition on the heuristic function. Can you guess what that condition is? So, let me sorry, HN less than equal to H star. What does this mean? This is the optimal cost solution, and algorithm is designed to find the optimal cost solution, and what we are saying here is that as long as the heuristic function underestimates the optimal cost, then it is going to be give you an optimal solution. So, as an exercise, I will ask you to construct a small problem. So, like this, which some leaf nodes, all nodes and so on, and you can basically manipulate the edge cost to make it underestimating or overestimating, and first work with an overestimating function, and you will see that it gives you some solution which may not necessarily be the optimal solution. Then try out with a underestimating function, and or you could go up and look up the past test papers. You will see one or two such problems there, where an Andor graph is given and you have been asked to find the solution essentially. So, do try it out at home. In the next class, we will take a diversion from here. We will move to games, primarily because I want to give the games assignment in early October, so that you can finish it by the end of October essentially. And then we will come back to this idea of expert systems, rule based systems. I mentioned things like R1 is called an expert system or prospector, how are they implemented, and what is a rule based system and how does it work. So, we will come back to that after we finish with games. Okay, so we will stop here.